Hello, my name is Mo Kari and today I want to talk to you about a novel in-car user experience based on audio augmented reality. But before I do so, let's have a look at iMuse, one of the first nonlinear music engines in gaming. Listen closely to how the music adapts as the player encounters a certain location in the gameplay. So, we have asked ourselves, can we transfer this experience of music that adapts to triggers in the environment to the physical world? We call the answer to this question SoundsRide. As you probably have noticed, the crescendo and subsequent forte were aligned with the tunnel exit. More generally, SoundsRide mixes music in real time, synchronized with sound affordances along the ride. We share some concepts with the related work, more specifically with context-adaptive music, procedural game music, automatic music to video alignment, and in-transit audio augmented reality. However, SoundsRide enables a real-time in-car music experience that is dependent on events along the ride. More specifically, we propose an approach for creating affordance-synchronized in-car music experiences by aligning music to estimated temporal distance. Our contributions include a design space of affordance-based in-car music AR, a method for deriving affordance-synchronized mix plans, and a recursive algorithm for incorporating continuously updated ETA information while minimizing audio signal manipulation. So how does our design look like? SoundsRide continuously estimates ETAs, that is estimated times to arrival, or estimated time to affordance as I call it, and then aligns music to these ETAs. For example, let's assume the next affordance on the route is a tunnel entrance. We know this from localizing the ego motion against the path, recorded and annotated by the user. From this path, we can also read out the ETA. In the mix plan, we then align the next event in the music, a beat drop in this case, to the ETA. Of course, once aligned, these ETAs can change and might prove quite accurate or not so accurate as we approach the affordance. Therefore, we must continuously fuse new ETAs and possibly resynchronize the music. We call this process microsynchronization. However, given the overall path with all its affordances, we can estimate ETAs to all affordances to come at once. Given this set of ETA constraints, we can compute an overall mix plan. That is, SoundsRide also aims at macrosynchronization. Let's get to a walkthrough. In summary, SoundsRide's approach to affordance-synchronized music mixing is based on continuous localization, mix planning, and resynchronization. After users record a GPS reference and annotate affordances along the path, SoundsRide can create an affordance-synchronized music mix in real time. On the SoundsRide localization client, we see the ETAs to all affordances along the ride. Using these ETAs, SoundsRide composes an affordance-aware mix of different songs and transitions between them. Let's take a listen. Okay, so let's take a closer look into how SoundsRide realizes its mix planning. Given a set of ETA constraints, we schedule snippets from a database containing user-annotated songs. We heuristically try to avoid silences during the snippet selection and try to overlap snippets. Based on these overlaps, the safe zones around a song event and some other parameters, we derive fade-in and fade-out times. Finally, we can mix these snippets into a single audio signal. Of course, we do all of this in real time while a previously mixed audio signal is already playing. We copy the updated part of the audio signal into the playback buffer. In so doing, we have mixed and resynchronized the audio signal with the environment. Unfortunately, there is one problem. But let's first consider an easy situation. When playback is still in the violet track, we can freely realign the blue track when ETAs are updated, as I've just shown you. However, resynchronizing a snippet that is already playing leads to a user noticeable artifact in the music. Therefore, we must try to minimize the number of resynchronizations. Given a previously planned ETA and an updated ETA for an affordance, we compute a set of deltas. We also specify some other parameters. Given this set of numbers, we decide on a resynchronization strategy, in particular, whether to accelerate or to delay the mix or to temporize with our decision. Okay, so let's hear it in action. First, let's take a listen to the mix planning, more concretely, a song structure-aware crossfade in Soundstripe that prepares the tunnel entrance. Note how Soundstripe respects the song structure and transitions to a demarcated segment in the next song. Next, let's fast forward to the tunnel entrance and hear the resynchronization. When approaching the affordance, note how Soundstripe first accelerates the mix to ensure synchronicity and then tolerates a negligible misalignment of less than a second traded off against another update. We conducted a user evaluation with 8 participants on a test route with 6 affordances. First, we investigated the perceptibility of Soundstripe and found that half of all affordances were recognized by users without being told about them. Second, we investigated Soundstripe's potential for immersion by evaluating the system in different criteria, including driving safety. We find indication that Soundstripe can negatively as well as positively influence driving safety. Thanks for your attention.